Hey guys, Mr. Smith here, and in this video lesson, we're going to talk about composite functions. So in our last two lessons, we learned about the sum and difference of two functions. In our last lesson, we did the product and quotient of functions, and today we're going to look at what happens when the final thing we'll do with combining functions when one function depends on another function. And we're going to call those composite functions. And to get started, we're going to think of an example from ecology, where the predator-prey relationship, where a population of predators in some ecosystem is going to depend on how much food, how much prey they have in the ecosystem, and in the same way, the amount of prey depends on the number of predator. So we're going to look at kind of a simplified example of a fluctuating rabbit population and wolf population. So let's say, for argument's sake, the number of rabbits in a wildlife reserve as a function of time, we'll call it R of t, can be modeled by R of t equals 50 times the cosine of 0.5 pi t plus 100. Let's graph that function first and identify some properties. Again, a nice thing about this unit is we revisit a lot of stuff we've done before. So here we're revisiting periodic functions. So we're doing the rabbit population. The axis is going to be r equals 100. So our rabbit population is going to fluctuate above and below 100. The amplitude is 50. So our rabbit population will go to a maximum of 150, a minimum of 50. The period we get by taking 2 pi and dividing by the k value, which is, in this case, 0.5 pi. 2 divided by 0.5 is exactly 4. And for this specific problem here, we are looking at the it doesn't specifically say that we're looking for the rabbits were introduced in say the year 2000 or something, and we're only looking at years after that. For this particular function, we know that t can actually take on any real number. We can plug in positives, we can plug in negatives, etc., to a periodic function, but we only get certain r values out. Our values for r, can I squeeze this in? R is an element of the real numbers. It doesn't work out very well. Here, I might say this. I might say this just so it doesn't look weird. R of t is an element of the real numbers, such that, and I'm going to squeeze this in there, the lowest the rabbit population can go will be 50. The highest it can go will be 150. Let's graph that and see why. So there's no phase shift here. So our cosine function is going to start on the vertical axis, and it will start 50 above the axis at that first maximum. So 150. The period is 4 years. So we'll come back to a maximum every 4 years, which of course means we would reach a minimum every 4 years, and that would be 50. Or sorry, a minimum halfway between that. So at 2 years, at 6 years, of course, every 4 years. I think I can get one more over here. And that means we would come back to the axis after year 1, year 3, year 5, etc., etc. So we got a fairly straightforward periodic function to sketch here, given the graph. Oh, one more there. Call that good enough. All right. Let's look at the wolf population. So our wolf population is going to depend on the rabbit population. So here we have a function describing that relationship. And if we think about what that means, the 0.2, that means 20%. The wolf population is 20% at any given time it's 20% of the rabbit population, but not the rabbit population at the current time. There's a bit of a lag, right? Like if there were more rabbits, then they'd be able to support more wolves, but it's not an immediate thing. It would take time for those populations to grow. Similarly, if you were to cull or remove, let's say, a large amount of rabbits, now there's not as many rabbits to support the wolves, and the wolf population would go down too, but it would take some time to have an effect. And that is illustrated here by t minus 2. We have a time delay of 2 years. And I think I can zoom in a little bit on my handout to make my writing a bit bigger. Yeah. Time delay of about 2 years. So this means, just putting that in words, wolf population is 20% of what the rabbit population was 2 years prior. Every wolf needs about 5 rabbits to survive. And as the rabbit population increases and decreases, it takes about 2 years for that effect of the wolf population to increase or decrease. Now, we actually know what the rabbit population is, or we know a function for it. So let's do our first example of, and this is a composite function where the wolf population depends, or the wolf function depends on the rabbit function. Let's simplify this equation, and then we'll graph it together as well. What does that equation say? Well, the wolf population is 0.2 times the rabbit population function, but not with t minus 2. So 0.2, and then I'm going to plug in our rabbit population function, which was 50, times the cosine of, I might actually need another set of little square brackets here. 0.5 pi t. But instead of t, we're plugging in t minus 2. T minus 2, close that bracket, plus 100. And now let's simplify things a little bit. We have 0.2 times 50, which is equal to 10, times the cosine of 0.5 pi times t minus 2 plus 100. And so now we have oh, and you know what? You have to forgive me. I just noticed this too. It's 0.2 times the entire rabbit function, which should encapsulate that 100 as well. Because I was thinking in our final one, well, how can the wolf population shouldn't be fluctuating around 100? It should be fluctuating around 0.2 times 100, which is 20. All right, this makes a lot of sense. Let's talk about why. The axis for that function, double equals 20. The wolf population is going to fluctuate above and below 20, which makes sense. That's 20% of what the rabbit population fluctuates above and below. And I will, you know what I might do actually? So I might write those properties in pink and then draw my graph in pink. Okay, draw on the axis. The amplitude is 10. Again, that makes sense. 20% of the rabbit population. The period is unchanged. The period is also 4. And our domain and range, the domain, t can still be any real number, but our range is different in this case. We're going 10 above the axis and 10 below. So the wolf population range, the wolves are an element of the real numbers, such that, and the wolf population fluctuates between 10 and 30. Squeeze that in there. Now let's draw it. We have to be careful here. Here we actually have a phase shift of 2 units. So normally our cosine function would start on the vertical axis. Here we're moving that right by 2 units, right 2 years. So normally we would have a maximum of 30, 20 plus 10, but we're shifting this right 2 units. So this would be our starting point here. And now we're good to go. We would have another maximum after 6 years and after 10 years. We'd have a minimum after 4 years, 8 years. I suppose I can even put at 0 years here as well. And we come back to the axis halfway between those. And we can see the wolf population fluctuating as well. And you may be asking, well, like, how can the wolf population be at a minimum when the rabbit population is at a maximum? More rabbits should mean more wolves, right? Well, it does, except it takes time for that kind of stuff to happen in an ecosystem. It takes time for the wolves to reproduce and have baby wolves and for that population to grow. But as that population is growing, they're eating more and more of the rabbits, and the rabbit population shrinks. And then by the time you have too many wolves for the too many wolves for the given rabbit population, there's not enough food, and the wolves start to die off. But then the rabbits start to increase because there's less wolves, and you have that constant interplay. But it's not an immediate thing. So a very neat application one of just periodic functions. But we have introduced our first example of a composite function. The wolf population depends on the rabbit population. So we have talked about the wolf population is a composite function. So let's kind of formalize what is a composite function. Composite function is a function that depends on another function. So I'll get this typed out. Let me choose an appropriate font size. That should be good. Composite function is a function that depends on another function. It is formed when one function is substituted in for another function. All right. Now we're going to introduce some new notation for you guys. So in general, when you substitute a function g into x, let me just pause. I got my kids outside. All right. This is why I don't usually record videos at home. You might hear the kids now and then, but let's try to move forward. So when you replace a function in for x, a function g, when you replace that in for x and a function f, we write it like this. We write, normally when we plug in a number, we're like f at 2 or f at x. Here we're going to write f of g of x. So we're plugging in a function into another function. We're replacing the x value with an actual function. And this is read f of g of x. So some new terminology. We're substituting a function into another function. And the order is important. This is implying left to right that we are substituting the function g into the function f, the first function. Now, some alternative notation you might see. This is our current notation we just introduced, f of g of x. You could also write that the following way. F that with an open circle composed g of x. This is an alternative way. It means the same thing. All right. So let's wrap our minds around this by actually creating some composite functions and just get a bit of experience replacing subbing a function into another function. So we're going to do 5 of these, and we're going to use some simple functions for f and g. The basic quadratic function, f of x equals x squared, and then a simple linear function, g of x equals x plus 3. So let's dive in. In each one, we're going to just graph the final result, talk about domain and range. But what you guys are going to see, for the most part, the functions we get aren't going to be crazy complicated, and we might see some old friends popping up. But yeah, let's dive in. So our first function, y equals f of g of x. So I'm going to switch back to my deep purple. Y equals f of g of x. So what does this mean? It means we replace inside the function f, we're going to plug in our function g. What is our function g? It's x plus 3. So in our function f, where there's an x, we're going to plug in x plus 3. Our function f was just x squared. So instead of x squared, we're going to plug in x plus 3. X plus 3 squared. And that's it. We have our first example there. Alternatively, I could write that like this. And then it's kind of like just personal preference about how you prefer to do this. The function f is x squared. So when I plug in that function g, what I'm doing is I'm squaring the function g. And of course, g of x is equal to x plus 3. It's the same result, whichever way you want to think about it. This one's not that hard to graph. It's a basic parabola shifted left 3 units. Vertex at minus 3, 0. Has the same shape as the basic step pattern. Well, it's very blustery here today. All right, and just a brief talk about the domain and range. That's pretty easy to see from the graph. The domain, x can be any real number. The range of this composite function, y is any real number such that y is greater than or equal to 0. But notice that the domain and range of the original functions, like the domain and range of g of x is x can be any real number, but the range of g is that y can be any real number. But when we look at the composite function f of g of x, the domain and range doesn't necessarily stay the same. So there's our first example. Let's try some more and just try to get better at this, get more comfortable. So part B, we're looking at g of f of x. So we're switching the order of what we're subbing in. So y equals g of f of x. All right. So what does f of x equal? Well, it equals x squared. So now we're replacing in the function g, wherever we see an x, we're going to plug in x squared. And since g is x plus 3, we replace the x with x squared. This composite function is x squared plus 3. Again, pretty straightforward function to sketch. It's our basic parabola, just shifted up 3 units. For the domain, x can be any real number. For our range, y can be any real number such that y is greater than or equal to 3. Which is interesting because that domain, y is greater than or equal to 3, isn't the domain of either of those original two functions. The domain of f of x is y values are greater than or equal to 0. The domain of g is y can be any real number, but the domain of this composite function is something completely different. Let's get some more practice, and maybe if you feel like, you can pause the video and try one of these on your own. But for part C, we're doing f of x. That's pretty fun. So we're taking the function f, and wherever we see an x, we're going to actually put in the function f. What is f of x? It's the quadratic basic parabola, x squared. And so where we see an x, we're going to plug in x squared. So that original function is x squared. We're replacing x with x squared. we have x squared squared, which gives us x to the power of 4. It's our basic quartic function, which, if you recall, has a vertex at 0, 0. End behavior, quadrant 2 to quadrant 1, also passes through negative 1, 1 and 1, 1. The difference between this and the basic parabola, though, is that, see how well I can draw this. It's a lot more flat. Not linear, but it's a lot more flat and squashed down, something like that. It's actually not too bad. And the domain for this guy, x can be any real number. The range, y is any real number such that y is greater than or equal to 0. All right, maybe, just maybe, you guys can give part D a try. We're doing g of x. So can you follow the same pattern? Again, if you don't feel like pausing the video and trying it on your own, you can always do it with me, but we're doing g of x. Where we have an x, we're plugging in the function g. So give it a try if you like, or follow along with me. G of x, x plus 3. So in that function, x plus 3, where there's an x, you're going to replace it with x plus 3. And we get this composite function, x plus 6. So kind of neat, when we did the composite, when the function was quadratic, when we did a quadratic function composed of another quadratic, we got a quartic function. Here we did a linear function composed of a linear function. We got another linear function. This function has a y-intercept of 6 and a slope of 1. I'm in Cami, so no excuse for me not to use a straight line tool for this guy. There we go. Now this is a line. It's a non-vertical line, so our domain and range, pretty straightforward. X can be any real number. In the range, y can be any real number. All right, let's continue. So for part E, we're finding, if I would just flip back, we are doing the composite function, the inverse of g composed of g. So for this question here, we got to find the inverse of g first. So I'll just make a little note here. First, we got to find what the inverse of g is. And if you recall our strategy for doing that from your grade 11 course, you're going to write it in y equals form, and you swap the x and y. X equals y plus 3. You solve for y. Y equals x minus 3, and so we have the inverse. The inverse of g is equal to x minus 3. And now we're actually ready to go about our problem. So we're doing the inverse, and we're plugging in g of x. Now, I'm going to do this one in the previous 3. In the first one, I showed you guys 2 different ways of thinking about it. And in this one, I'm going to focus on doing the second way, just to give you a variety and just a mixture of experiences, and you can kind of choose the method you want to use. So the inverse function is x minus 3. So that means we're doing g of x minus 3, which is just x plus 3 minus 3, and we get x, which is actually very interesting. This is just the basic linear function. Add a few points here. And I'll use my straight line tool. And because it's a line that's not vertical or horizontal, again, domain and range, pretty straightforward. X can be any real number, and y can be any real number. Now, this idea of plugging a function into another function can take a bit of time to get used to. So you'll have we've done 5 examples here. These 5 examples I have done, I've used the same examples that the McGraw-Hill-Ryerson text uses as well. So feel free to peruse that chapter if you want to when we're done and look at the same examples. Everybody has their own personal style and flair, so you can see how the textbook does it, and just to reinforce things if you'd like. But you'll get a lot more practice when we're done our lesson. Okay. So in our next example, we're going to learn how to evaluate a composite function. So in part A, our goal is to evaluate u of w at 2. And there's a couple ways to do this. The first way, we could actually find the composite function, u of w of x, simplify that equation, and then plug in 2. Let's do that now. So u of w of x, this is my preferred method, is to plug in what w of x is equal to, and that's 1 over x minus 1. And so now my function u, wherever I see an x, I'm going to replace that with 1 over x minus 1. So I have 1 over x minus 1 squared plus 3 times 1 over x minus 1, and then plus 2. And there we go. Now, we could simplify. However, if our goal is just to find out what the value of this function is when we plug in 2, then simplifying isn't really necessary. Let's just plug in 2 and see what we get. So u at w at 2 means let's just plug in 2. So 1 over 2 minus 1 squared plus 3 times 1 over 2 minus 1 plus 2, and we'll just work it out. 2 minus 1 is 1, so we got 1 squared. 1 over 1 is 1. We also got 1 over 1 and plus 2. 1 plus 3 plus 2. We get 6. That's one way we could do it. Again, not necessary to simplify that composite function if our only goal is to substitute in a value. What we also could have done is we could have found out, well, what is w at 2? We could have done that first. W at 2 is equal to 1 over 2 minus 1, which is just equal to 1. And if w at 2 is equal to 1, then if you were finding the value of the function u at the value of w at 2, well, this is just equal to u at 1. W at 2 is equal to 1. So you could plug 1 into your function u, and let's see what we get. So u at 1, don't need that. That would be 1 squared plus 3 times 1 plus 2. 1 plus 3 plus 2, we get 6. Which method is better? Kind of maybe depends on the question. Like each one can be useful at times, and you kind of just need to pick something that works for you. Obviously, I think in this question, method 2 is probably a bit more efficient. Takes a bit less time. But you have those two methods. For part B, I invite you to try either of those methods. I think for myself, I'm going to use our method 2 for part B. So let's dive in. We're doing w at u at minus 3. Might just write that down really quickly. W at u at minus 3. And maybe off to the side, what is u at minus 3? Well, let's find out that first. So the function u is x squared plus 3x plus 2. So we'll plug in minus 3 squared plus 3 times minus 3 plus 2. Let's work this out. We get 9 minus 9 plus 2, u at minus 3 is just equal to 2. And now we're ready to go. W at u at minus 3 is just equivalent to w at 2, because the value of the function u at minus 3 was 2. So we're finding w at 2, and the function w was 1 over x minus 1, 1 over 2 minus 1. We get 1. In my opinion, probably a bit more simple than finding the actual composite function. Although, you know what? Got some time, so maybe I'll just like squeeze this in here. What is that function? W at u at x. Just calling an audible here. This could be worthwhile doing. So we're finding w at the function x squared plus 3x plus 2. And the function w is 1 over x minus 1. So where we have an x, we would plug in x squared plus 3x plus 2. Of course, we still have minus 1. And this actually simplifies pretty nicely to x squared plus 3x plus 1. And when you, if you were to plug in negative 3 into that, you would get 9 minus 9 on the bottom plus 1. And you would get 1 over 1. You would get the same thing. You know what? Why don't I just carry it to completion? U at minus 3 would equal 1 over minus 3 squared plus 3 times minus 3 plus 1, which just equals 1 over 1. And either way, you get 1. You can kind of pick which method that you like best. All right, let's continue. I think this is our last example. Yeah, we're going to wrap things up with this. And we're going to just solve this question mostly in Desmos. And create the equation for the composite function afterwards. So here we have the number of CDs in thousands sold, and you guys might be like, what's a CD? But you've probably seen a CD before, but most people don't buy CDs anymore. I don't know if anyone does. Certainly not cassette tapes, but we have the number of cassette CDs sold is we can see as quadratic. The number of tapes sold in thousands we can see as a linear function. And we're going to treat t equals 0 to be when the store opened in 1990. So let's just graph. I won't worry about up to the year 2008, but let's graph these two functions. So I have Desmos opened up here. And I'm going to change my window settings in order to make sure I get everything in here. So I'm going to go from minus 1 to, I'll go to 20. That should get our 18 years in there pretty good. And then for the y-axis, I'm going to go from negative 1, so that'd be like negative 1,000 to 10. And I think that should be pretty good. Let's graph our two functions. So I am going to have to replace t with x. So c of x, negative 0, negative 0.03 x squared. Of course, we know what to expect here. It's going to be a parabola. It opens downwards. Plus 0.5x plus 3. So what we can see is, in the year 1990, the initial revenue this is the number of CDs sold. So we sold about 3,000 CDs. And this trend continued to increase and increase and increase, people buying a lot of CDs. And then somewhere a little bit past 1998, we reached a maximum of selling about 5,000, just over 5,000 CDs every year. And then after that, the number of CDs sold starts to drop. Of course, you probably all can think of a reason why the number of CDs, the sales started to drop. It's because the new wave of MP3s and digital music started to come into play, and we're buying less CDs. If we draw the tapes function, capital T of x was 1.5 minus 0.1 times x. So no surprise there. Its initial value, 1.5. So 1990, 1,500 tapes sold. And already by then, the trend for selling cassette tapes was decreasing because more people were buying CDs. But you can see that actually this decreasing linear trend by t equals 15, so 2005, virtually like nobody is buying cassette tapes anymore. People are just buying CDs. The cassette tapes have essentially become obsolete. I had a cassette tape player in my 1998 Honda Civic up to when I sold that in about 2010. So I still played some. I had like mixed tapes lying around. But anyways, I digress. So we can kind of see the trends. CDs increased in sales until, again, about 1998, and it started to decrease. Tapes just steadily decreasing until about 2005, and nobody's buying tapes anymore. So let's head back to the lesson sheet. So part A done. In part B, we have an equation, a composite function that gives us the revenue. The total revenue depends on the number of CDs sold, and it depends on the number of cassette tapes sold. And those two things are functions of time. So our revenue function is a composite function of two actual functions, the CD function and the tape function, times 1.04 to the power of t. Let's find an equation for this guy, and then we'll graph it a couple of ways in Desmos, talk about what it means, and then we'll call that a good day. All right. R at t is equal to, okay, so 3 times the cassette function, which is negative 0.03 t squared plus 0.5t plus 3 times 2, plus 2 times the tape function, which was 1.5 minus 0.1 times t, and then times 1.04 to the power of t on the outside. And maybe as we simplify this, you can have a little think on what why we would have that 1.04 to the power of t on the outside. Let's just do some simplifying here. I'll take my time and just distribute the 3 into the first bracket. 0.09 t squared plus 1.5 t plus 3. Distribute the 2 into the next bracket. That's plus 3 minus 0.2 times t. Of course, everything multiplied by 1.04 to the power of t. I might just illustrate. That's what I did there. Okay, and then we're done. Let's just clean that up. I like to put my quadratic terms first. So negative 0.9 t squared can stay where it is. Let's collect the t terms. 1.5 minus 0.2, that's plus 1.3 t. 3 plus 3 is 6. All times 1.04 to the power of t. All right, so we've got our composite function simplified. This is the this is our revenue function. It's a product of a quadratic function and our exponential function. A quadratic because we added a quadratic and a linear, which gives us quadratic. And if you're wondering what the 1.04 to the power of t on the outside is, well, if all things stayed the same and you sold the same number of CDs and the same number of tapes every year, your revenue would still go up because generally, because of inflation, prices just continue to go up every year. And that 1.04 to the power of t just represents 4% inflation. All right, let's sketch this guy and just talk about any trends we see, and then we can call the lesson complete. So there's 2 ways that we can sketch this function, and I'm going to show both ways. The first way we could do this is by actually just sketching our simplified function. So we found that this revenue function was negative 0.09, and we're using x instead of little t, plus 1.3 times x. Oh, I think I made there. Yeah, I did. So if you've been screaming at your computer, as is my habit on occasion, 3 times 3 is 9. I can math. 9 plus 3 is 12. Okay. I thought something was looking a little fishy there. Plus 12, that looks better. We have our 1.04 to the power of x. I think I have everything in there correctly. Now I am going to have to zoom out a little bit here to get everything in. I like the x scale, but for the y scale, just doing some mental math, 3 and 2, our y scale, let's go up to like maybe 30 or so. Okay, yeah, that worked pretty good. Actually, it gets everything else in there pretty good too. So we can see the revenue function. It started to tail off a little bit as well once the number of CD sales dropped. But you can see the maximum revenue didn't exactly correspond to when the number of CD sales was the max. That was around 1998. The revenue kept increasing due to inflation up until about 10.6 years past 1990. So now we're into the year 2000 is when revenue peaked. And then you can see the revenue starting to take a dive when MP3s became more popular and people aren't buying CDs, people aren't buying tapes, revenue dropping and dropping and dropping. And these kind of stores had to adapt and sell different things, move into DVDs, move into collector's items and that kind of thing. Now, just to wrap things up, the Desmos can actually graph this a second way. So if we graph the revenue function, and remember the revenue function was 3 times the cost function, C at x, plus 2 times the tape function, and then times that exponential 1.04 to the power of x. And you can see it's the exact same function. So Desmos is really cool like that. 2 different ways you could have graphed that composite function. Both work, and we've actually just verified that our answer for that simplified function was correct. Okay, so today we learned what a composite function is. If you are making use of the McGraw-Hill-Ryerson text, they do have a little error in this visual. To get the function f composed g of x, you first have to evaluate the function g at whatever x is, and then you evaluate the function f with whatever g at x was. So they just had the f and g swapped there. We did 5 examples of this. To determine an equation for a composite function, you substitute the second function into the first. We looked at kind of 2 ways of thinking about that. And we looked at 2 ways to evaluate a composite function at a specific value. You can simplify, or you can evaluate the second function and then plug whatever you got into the first function. As usual, I've got some suggested practice for you guys. And for the people taking my course in we're now in the winter of 2022. That is the last video lesson. So yay me, I get done making 3 or 4 videos per week. But yeah, got some suggested practice. Hope you guys enjoyed that lesson. I enjoyed giving it. Please reach out if you need a hand with anything. Take care, guys. We'll see you soon.